Okay, so this is part 2 of module 2 for stats 2. And in module 1, we talked about scatter plots and correlation. Now what we're going to do is we're going to move from correlation to actually doing the regression modeling. We're going to start with simple regression with one variable and talk also about model diagnostics. I'm pretty sure this part 2 video is going to be in 2 parts, A and B, because I don't want to go over like half an hour, 40 minutes, and I have a feeling there's no way we're going to be able to do it that short. Okay. So again, the discussion from the first part of Mod 2 is we're now jumping to working with bivariate data. We're also going to go into multivariate data. That'll be part 3 of Mod 2. We're going to actually talk about multivariate modeling a little bit. Don't be intimidated. It'll be okay. We're just doing a little bit of it. But univariate statistics is kind of boring. I mean, you're just working with one variable and you're just learning basic stuff and it's just, it doesn't get to like the level of excitement per se. Bivariate is when you're looking at two variables. Now, this is the data set and it's like the same row and it's usually like the same ID or the same person or the same transaction. And then we have multiple things measured, like your height, your weight, your GPA, your income, where you live, and all that. And so we can look at how the variables relate to each other. Okay. Typically, we go and we look at two variables at a time because it's too difficult to like look at like a whole bunch of variables. There are actually techniques for correlations with multiple variables involved. You like hold certain like partial correlations and stuff like that. We're not going to get there in this class, but they do exist. And then multivariate data, which is stuff like this, typically we'll break it down to look at the bivariate relations, but also we're going to do a little bit of regression modeling where we throw in multiple variables and see which ones are the best predictors. Not just, not just one variable predicting things, but often like, your income, for example. You might want to predict your income not just based on your years of experience, but also maybe what your degree level is, things like that. So you often would want to use more than one predictor when you're doing a regression analysis. Okay. So the relation between two variables, this is from the correlation thing. We're mostly concerned here with looking at linear relations. There are methods for working with other relations, but we're not going to get there in this class. But yeah, so, and then what we did is we measured the relation with a metric called the correlation. The scatter plot is to just look at it. A scatter plot, you're just visualizing what's going on. And then you can actually use this metric called the correlation, which is R is the sample statistic, rho is the formal population metric. And this is calculated from something called the covariance. We don't directly use the covariance because it's incredibly confusing and the covariance metric is not standardized, so like you would never be able to interpret. Like if somebody told you the covariance is 200,000, you would really have no idea what that actually meant. So that gets standardized to this metric called the correlation that we can understand, and a correlation value-wise is between -1 and 1, and the absolute value of the correlation, the closer it is to 1, the stronger the relation. Minus just goes down. Negative correlation, one variable up, one variable down, and positive, the two variables are going up together. So that's a correlation metric. You always have a correlation metric. I hear from people, oh, there's no correlation. There's no such thing as no correlation. You have two quantitative variables, you have a correlation. You can calculate it, it's there. Whether or not it's significant is a different issue, but there still is a correlation. Now we have like what your textbook likes to do, which is like put way too many words in a small place. But what this is saying in English is that you got to test your correlation metric, and our last video showed you how to do that, and you want to have a p-value less than 0.05. And then when that happens, you can go on to regression. Okay. This is like textbook stuff. Now, there is some possibility that you're just spontaneously getting a p-value less than 0.05. That's not really that likely, so yeah. Then there's this complex interrelation between variables. The manatee example was actually a good one of this because we have dead manatees and then we have population and boats. Population and boats are probably very, very related because more people, more boats. So you do have this kind of like more complex interaction going on there. And that's also relates to, these are kind of sort of the same thing. Like the third variable, the increase in deaths might not be because of the population. It might be because of the increased boats. Okay. The cause-effect relation is not determined here. Correlation does not determine cause and effect. We don't know what causes what, we just know that they're related. Cause and effect are determined by empirical science and doing a treatment and control group and doing a formal clinical study type thing. Okay. So a correlation, we're going on the fact that there's a relationship. It's not necessarily that one thing causes another. Like we could predict your height based on your weight. Your weight doesn't necessarily cause your height. So that's a different kind of, that's what the relationship means. Okay. So, but if and only if you get that p less than 0.05, right? Remember the test is that rho, the correlation in population terms, is 0 versus it's not 0. You want to have that it's significantly different than 0, and you want to have this p-value less than 0.05. Then you can do a regression model. If you don't have the p-value less than 5, you quit, okay? You don't actually model something like this, and people do all the time because they didn't take my class and they don't know any better. If you have a low correlation, there's no convincing evidence that the relationship is, that there's a strong relationship. And if there's no strong relationship, you don't go start predicting one thing based on another if they're not related to begin with. It doesn't make any sense. At least not to me, it doesn't. Okay. Now, once we have our p-value less than 0.05, we can do this. We can do a regression. Now, this is part of why you spent a million years in high school algebra learning y equals mx plus b. They spent so much time on that. I used to teach high school math. It's ridiculous. Like, we literally spent in algebra 1 like 3 months on it. But anyways, this is an expansion of that when we do a regression model. What we are doing, and this is actually a really nice, it's not just pretty, the colors, it's a very important slide. I kind of wish they did this in stages. So like I kind of wish they started with just the scatter plot. So we have the scatter plot. I'm going to kind of do it in stages. So we have the scatter plot. Okay. And then what this is doing, I'm actually sketching sort of the same little dots in. So this is kind of like the dot pattern, like these are these. What it's actually doing is the observed values of the data. So these are the dots. These are our actual data values. Then what it's doing is it's literally putting what's called the best fit line. Okay. And literally for that particular data set, there is one and exactly one best. It is the best fit line. It is not a best fit line. It is the best fit line. So a regression line is literally the one and only line that fits the best between the data by minimizing, and all it's doing is it's minimizing the distance between the data and line. If you think about it, like here's the points, data points. There's one line that will minimize these distances from the points to the line. Okay. And that's our line of best fit or our regression line. Okay. It's really that simple. It's not super duper complicated. We're just taking our little points, right? And we're fitting the line that minimizes, it will minimize the average distance of the points line. That's what it's doing. Okay. That's what's called a line of best fit or a regression line. And so D, what this is this is just the distance of the points to that. You want to actually minimize these. Okay. And then the line is the blue line, and the little dots are just like the distance from the point to the line. Okay. The difference between the actual and predicted value. Now this is called the predicted. The line is the predicted. Okay. And the data points are the actual. Now for X, it doesn't matter because for each point here, X is the same. Like this is the same value here and here for X. But for Y, Y has two values now. It has an actual Y and a predicted Y. Sometimes we call this Y hat for predicted, okay? And so they do Y prime. I actually like Y hat better. So this and this Y are two different things. We have the data Y and then we have the line Y. In most cases, in rare cases, the data Y and the line Y will be exactly the same. But so for every X, you now have the data value of X and the predicted X. Okay, get that? So the difference between the actual and the predicted is what's called a residual. These are the distances between the point and the line. Okay. These are also called like error terms. They're not really error terms. I like the idea of residual better because they're not really like, I don't really like thinking of them as quote errors. There's nothing like mistaken about them. And the method that's used, there are actually different ways of doing regression that we're not going to get into, but the method typically taught in intro class is the method of least squares. And literally it's determining the least distance using a method of kind of similar to the way the standard deviation is calculated. You square and unsquare things. Okay. There. So that's the basis of what a regression line is. You're literally fitting a best fit line through the data, and the distance between the point and the line is what's called the residual, and then the y values do have the predicted and the actual values. Typically, these are different. There's occasionally, like you see one point here where it might be awfully darn close. But yeah, regression is my world, for the most part, because this is really what a lot of what applied statisticians actually do. And yes, I have a master's specifically in stats and a doctorate in quantitative research. So you know, regression is huge, man. This is unbelievably big because what regression allows us to do is predictions, okay? So, and even if it's over time or whatever, like you have like sales data here and you can make a model and you can predict like future, you know what I mean? So like business and stuff, this is huge. It's huge to be able to take your existing, you build your model based on data, and now you have a mathematical model, which for simple linear regression is just y equals mx plus b. You just need a slope and an intercept. And now you have something to predict the future. Yeehaw! You know what I mean? Um, a lot of statistics, um, a lot of statistics in what master's level statisticians do is this. Now, psychology student people, you're probably not going to be doing like, unless you go in your doctorate, you might do a doctorate like actually developing a prediction model for something. That's not like an uncommon thing to do. Like, determine like, who might develop like some psychotree disorder. I don't know. I'm just making stuff up. And so you would have data and you would try to do some predictions and do some modeling based on that. But you guys will use this and you'll actually be using regression models that other people have made. Like when you try to predict like maybe you're working human resources and you're trying to predict who would be a successful employee, and you might have some weird algorithm where you input applicant characteristics and you give them like a score as an output. The output score would be produced by something like a model. When I use the word model, is regression model and those are the same thing in my, so I kind of like interchange the words. I generally use the word model for like every kind of like statistical model. Um, yeah. But anyways, this is kind of the world as a statistician. It's not as like I mean a clinical psychologist would probably not in their daily life be making regression models, but they would be using existing regression models for prediction purposes. And so understanding this is kind of important. I originally made these slides during COVID, and these are some COVID models that were trying to predict like how many COVID cases there would be like over time. Um, so these are examples of um, forecasting is another sort of like term for this. Often, a lot of times, not always, but particularly in business applications, you're doing stuff over time. There is a little bit more to doing these. If you're doing stuff over time, you often have dependent observations, and so you do actually call it a time series. And there's all kinds of different, more advanced modeling techniques. We're just doing baby stuff here. Yeah. So then we go back and we go to the textbook, which, I kind of have a love hate with. So this would be the formula for a line like this, okay? And it's y prime because this is y prime. The y values are the data value. So y prime is the line. I like to call it y hat because that's what I learned. And then we have the slope, which we don't call m. You know how like in algebra class, this is m? We don't call it m, we call it b. Now that's going to make you super crazy because the intercept we call a, and you're used to the intercept being called b because y equals mx plus b, okay? In stats land, this is y prime equals bx plus a, which we also like to muck around and write this way. So the letters aren't consistent, and it's even worse because the slope in statistics is the same letter that you use for the intercept in algebra. Sorry. But what's super important about these formulas, and again, I'm not really a classic algebra girl anymore. Very much like the correlation coefficient, if you look at these, the only thing that you need to calculate these is x, y, and a sample size. That's it. Okay. Regression is kind of an old, a lot of statistics and data analytics stuff is actually really fresh and new. Regression is actually one of the older topics, and a lot of the stuff in regression was actually very hand doable. Is that a word? Hand doable? I don't know. So you can very simply, I mean, it's just a matter of just not messing up your details of your calculations. You can very simply do out a little table and use these formulas and plug all the numbers in and calculate the slope and the intercept without a computer but we're not going to do that because we paid for SPSS. Okay. This is the example in the book. This is also the example in the old example videos. I'm going to do a different one today because I want to do the manatee ones. But in the other videos, and I'd rather you actually have two examples anyways. In the classic older videos that are just like the step for like each individual thing, this is the regression model done on those, which is consistent with the one in the book. This one was also in the last slides, I think, for a hand calculation of correlation that turned out to be like 0.98 or something. Um, yeah, so here it is again. So this was the correlation from the last stuff. Then what they do is now this is like all summarized, So then what they did is they calculated the slope and the intercept. And then what they do is they stick them in the line because y prime equals a plus bx. A is equal to 0.396. This you should have done a lot of in high school algebra class. Okay. So you get the values for the slope and the intercept, and then you substitute them in, and you need to have these specific values in the equation, and you should understand what this is. This is the equation of the regression line. It has this for a slope. It has this for an intercept and this for a slope. And you should be able to plug in a new value for x, which in this case is, I don't know what, cars. So like you should be able to plug in like 50 for cars and solve for y, and that's high school algebra, so I'm not going to review that. But yeah. And then we have even better. See, this stuff, I like this. So here we have the data plotted out, cars and revenue, and the dots correspond to these guys, 63, 7, like this kind of stuff, like that. That would be the 63 and the 7. Um, and then the line is fitted for you. This is the line. It has the slope and the intercept in it. Slope of 106 rather. That would mean that like for every increase in car, the increase in revenue is like 0.106 because that's what a slope is, a unit rate of change. So that is our regression model. Now we could take this and we could predict out if we had 110,000 cars. We could stick 100 in, right? And 100 times 0.106 is 10.6. And we would get 10.969, and that would be our predicted revenue. And that would be cool. This is why business loves these things, people. Everybody wants to be able to predict how much money they're going to make next year. Okay. And so this is doing what I just talked about. Now they did 200,000 and they're predicting that this would be revenue. No, well, no, I did like 110,000. So mine is like sticking 100 in here. They're sticking in, I don't know, 20 or something like that. But same idea. You should be able to use those and do that. So the magnitude of the slope is what's called a marginal or unit change. That's actually, if you ever study calculus, and you probably don't need to, but if you ever do, that's a derivative as well. So yeah. One thing about these models, which is actually a good thing because it's like job security for me, they go stale like bread. So your model, specifically is over time, it's really, really good. Like here's the data that you actually have, and here's your model. Your model is going to be like really, really good for like, let's say that this is over like 5 years. Your model is actually going to be probably pretty good at predicting the next 2 years. But if you try to use this model for predicting 10 years out, it's going to suck. Okay. And you can see this kind of like fan of uncertainty. So the predictive accuracy of a regression model, they work better if they're closer to the existing data. Once you start kind of going to fantasy land and trying to use a model for predicting things much further out, it matters. Now, in psychology, this would matter for something like if you built a model on like adolescents or like young adults, like 16 to 25. It might work pretty well for a 28-year-old, but it's probably not going to work for like a 55-year-old. So, like, the kind of implication there is like models are kind of developed for the data that they're developed based on, and they're actually really great for predicting values that are like close to that data a little further out. But if you try to predict something really far out, you're going to get a bigger and bigger fan of uncertainty. We're going to look at something called a prediction interval soon, and that's what this is. Prediction intervals will give you like how much uncertainty there is in your prediction. So I do want to look at those. They're kind of, they go along the interval estimate kind of thing, low end, high end, like confidence intervals. But models are only so good as their predictive accuracy. So, they're pretty good at doing known data, relative, things that are relatively close, but not things that are super far out in the future. So what you have to do is you have to constantly update your model, like, and you have to constantly update a new model, as the old one becomes outdated, which gives the statisticians something to do. Okay. Then we have this issue of outlier inferential points. Again, it's much more of an issue with small data sets, like those in textbooks, which is one reason I don't particularly love textbooks, because in the real world, I mean, in a textbook, if I had a little situation like this, see this? And then I had like a point way out here, this would be a really influential point, because this right here would be what we call an influential point, because what's going to happen is the line would have otherwise gone this way and it's going to go this way because of this one little point out here. However, if we have something like 10 billion, if we have just billions of data and then we have like one little point out here, who cares? That point is not going to have any leverage or influence on the rest of the model anyways. I mean, you might want to exclude it, but realistically, it's not going to affect things. Whereas if you have a small data set, one little outlier can like really kind of mess everything up. That's basically the issue here. Okay. Generally speaking, you would not make a statistical model on 4 data values anyways. Um, you know, and you could, like, for simple business purposes, like if you have 4 years of data, you might be predicting the fifth year out, but you would not make like a psychology model predicting behavior that would be used by the federal prison system with like 4 data values. You'd have like thousands in there, unfortunately, because that would mean there's thousands of criminals. But hey, um, assumptions for predictions. Now, I won't generally test you on like the sort of theoretical stuff, but because I care more about the applied stuff. But what we're going to assume as usual is that our samples are random and not biased. For any value of x, the value of y will be normally distributed about the regression line. That's actually what they're illustrating here. Again, this business of everything being random and normally distributed is important. The standard deviation of dependent must be the same for each value of the dependent variable. What that's saying is that if I have like x, y, 2, 3, that's saying that we don't want to have like, let's actually do years. So let's say this is year 1, year 2. And this is like sales. Okay. And this is like 10 and 20, but we don't want to have for this, like, we don't want the standard deviations to be like super crazy. So, like, we don't want to have sales in like one year being like that, and then sales in the other year being like way all over the place. Um, that's sort of like the issue when we did 2 sample t-test and we had to test with the Levine's test to see if the variability was different in the different groups. I mean, in this class, we're going to kind of like not formally assess this. If you were a statistician, of which I basically am, I think so, after having 20 plus years of a statistics degree, um, the way that we cover this in this class, if you're a formal statistician, you do spend a lot more time checking your data and looking at these assumptions and things like that. So, and if you're publishing and things like that, there is more sort of theoretical checking statistics behind the scenes. But so this is just sort of like, I mean, if you don't understand these diagrams, to be honest, like this diagram is just kind of a little crazy to me, but that's what that's doing. So there's a little bit more to just like, doing regression models in terms of like what your data has to be, and that's because you want your models to be statistically like robust and reliable. You don't want to have like potholes. Now the issue of who's x and who's y. X is independent, y is dependent. That's a relation always. So you have this, whatever this is, x, you're modeling y based on it. So y depends on x, and you're going to model y on it. Now, in correlation, it didn't make any difference. You stick in x and y, you're going to get the same exact measurement no matter what. You stick x and y here, interchange them. The R value is going to be the same because it doesn't matter. R is measuring the relationship strength. Doesn't make any difference which way it's going. When you're doing regression, it does matter. Not always. Some cases like height and weight, you can flip them. I mean, predicting height based on weight or weight based on height, I don't know what the difference is. So you could actually do 2 different models. This relation is often a matter of thought. Now, if x is time, x is always going to be an independent variable. You do not predict time. I mean, that's just weird. But in some cases, like height and weight, which one's predicted on which, I don't know. But when you run regression, you do want to make sure that that you know what your dependent variable is. Now, independent, right now we only are going to have one, but we're actually going to have more than one in the next stuff that's coming. So, life is not going to be boring around here. Okay. So if you want to predict in some cases, like if you wanted to predict test scores based on hours of sleep, it would only make sense that test scores would be the dependent variable. That's what you're looking at. You wouldn't like predict. I mean, I don't know, maybe you would, but Usually there's some type of relation that actually makes a lot more sense. Okay. Yay! So let's now go into regression. This car model one, this is the one in the book. This is the old video, so that's still up. I'm not going to do that one because it's boring. There is still the other video on that, and the data is available for that, I think. And even if the data is not available for that, in some cases I mean, and I don't give you the data. So this is the data for the car model if you want it. And you actually should be able to go in and type this in. You don't even have to type in the company. You just need X and Y. And you could run this and just double check that you're getting the same exact model and that you understand what you're doing. And so that's there for you. So I'm not going to redo that one because it's boring to just do the same one over and over. I am actually going to go into SPSS now. And this is going to be the end of the slides for this part because I know this is going to go like way over otherwise. And I'm going to go into SPSS. I'm going to go to the manatee stuff. Now, this is the stuff that we did in the correlations as well. And in the correlations, we've already done the correlations. I'll rerun those quickly. But so this is the manatee, and then it's each year, and then how many dead manatees there are in boats and population and water temperature. So I'm going to let's run the correlations again, just the correlation metrics, not everything else. And I ran these, and we did the correlation metrics of the variables. Okay. And then it gave me the output, and I looked at this. Now, what I want to do is predict deaths, okay? So of these variables, the strongest one and the biggest correlation is boats, okay? So that's what I'm going to go for my regression model. I am going to predict deaths based on boats. Right now we're just in a X and Y situation, and we're not going to deal with population water temperature yet. I may use this again in the multivariate stuff that's coming up. But so I looked at the variables that I have, and the best choice model is clearly, if I have to pick one, I'm going to predict death by boats. Okay. So how do I actually run this regression model? Because inquiring minds want to know. Death is my y or dependent variable. Death is dependent on boats. Okay. It would not make any sense to predict boats based on deaths. That would just be like there's a weirdness to that. It's not really a sensible model. Okay. Anyway, so how do we run a regression model? Let's learn something new today, shall we? Okay. General linear model, people. Now, this is really, I have to tell you that a lot of this, like almost half this remaining stuff, is actually different models. No, we're not going to go there in this class, but this is why there's entire programs of master's degrees in statistics. And yes, I took, I think, 36 credit hours or 12 graduate courses just in modeling techniques, literally. So, but the simplest one, and all I'm going to sort of torment you with, general linear model univariate, okay? Or regression, actually. No, there's actually linear regression. Let's do this one. Regression linear. Let's do this one. Um, we can do this one for this, but here's the deal. When we go into the other one, we want to do this. But we're not there yet, so let's not worry about it. So for now, let's do regression linear and use this one. This one right here and this are basically redundant, but let's do this one first. Okay. So I just pulled up the regression, linear regression. I have to identify my independent and dependent variables. My dependent variable is death. My independent variable of choice is boats. Okay. Notice that this will actually let you enter more than one variable. Don't do that yet. We only have one variable. We're doing a simple linear regression. This will do plots, but I don't think it will just do a scatter plot. These are actually residual plots. We're going to get to these really soon, but not now. And so this is just going to do deaths and boats, X and Y. Okay. And then I just hit go. Bam. And you're like, what is all that stuff? This you don't have to worry about for now. This I'm going to talk about soon. This is something called R squared, which basically measures how good your model is. ANOVA is something we're going to learn later in the course. So we basically omitted this one, and this one. So you're like, what do I have to look at? And the answer is this. This is what you want to look at. This is your regression results. Okay. And you're like, what is that? Well, this is, there's a couple things going on here. This right here, these are your like model things. Now, it's super confusing what this is. Um, because it doesn't tell you like which one's the intercept and like which one's the slope, and you're like, ew, I know. Let me actually I don't want to like overcomplicate my life, but I'm probably gonna do that anyways. Um, let me see if I can. Okay, I'm gonna make a mess of my PowerPoint show basically. Because I want like a blank thing. I can't write on SPSS, by the way, so that's why I'm doing this. You're like, what? Okay, so this mess, I can't get it to look like the table. I want it to look like the table. Um, there we go. It looks like the table. That was paste picture, by the way, because you might want to, like, you're going to be doing projects and you're going to want that. Okay, so this is what the SPSS output looks like. And you're like, what the heck is that? Okay. So this right here, this is your slope and your intercept, except it doesn't tell you it. The intercept, so let's do y prime equals um a plus bx. That's the statistics way of writing mx plus b. Y prime is equal to negative 49.05, because I'm going to round that, plus 1.406 times boats. This is your intercept. This is your slope. Okay, and actually should have left this as x for now. Now, I actually prefer that you write them like this. Des. Like, in other words, when I write a regression model, I don't just use x and y. I just actually write this. There we go. There's your model. That's equals negative 49.05 plus 14.06 times boats. Now we can stick in anything we want for boats, and it would give us a prediction of how many people are going to die, which is depressing, but, you know. Anyways, so those are your actual model things. The other thing to look at is these. Significance. You want to see p-values less than 0.05. If your p-value is not less than 0.05, it's not a good model in general. Like, whatever you're entering, this is sort of goes along with the correlation not being significant. Typically, I think always, I'm not actually 100% sure about that. I think always when your correlation is significant, you're going to get this significant too, because this is looking at deaths and boats, and this relation has to be significant. Okay. Um, so this should be less than 0.05. If it's not, you basically have a rotten regression model. Again, not everyone looks at that. So for a basic regression model, that's it. Like, that's how you get your coefficients, and then that's how you write your model. And then you should be able to plug a number in for boats and get a result that makes some kind of sense. Okay, cool. You're like, are we done? Um, Yeah, with this part, definitely. We're done with this part. Now, I made a big mess of my slides, so excuse me on that. Somewhere in here, we're not going to talk yet about this because I'm going to close out this video and do another one. There's actually some additional ones in here. Let's do one more. I put in some extra practice ones because I do want to do one more. So let's do, these are tough in the sense that both of these, murder and robberies and murder, like, these are, I think these are from the book, but these are two situations where, I mean, do you predict robberies based on murder or murders based on robberies? I don't know. It's a tough call, people. Oops. Anyways, I can't just copy that, which, I get, like, I'm a lazy person, so I want to be able to just copy that. Let's do one of these. I don't want to do both because, like, there's too much to do. And you have a whole bunch of homework problems on this. And so when we're done with this video, you're going to be all set to do problem set 2A. 2A, people, 2A. All right, well, that defeated the purpose. Okay, here. So I'm going to do this murders and robbery thing. I think I have this somewhere else, and I'm going to pause because you don't want to watch me enter the data. That's going to bore you. Okay, so I've entered my data because I didn't want you to sit there and, like, watch that, because who wants to watch people enter data? But no, I lost my data. Okay, so I've entered my murder and robbery data. Okay. I don't remember what the results were for this, by the way. It's much more fun if I do videos without practicing everything ahead of time. I never do. I do so many videos a week that literally, like, I probably spend on average 25 to 30 hours a week making videos. So if I had to, like, actually practice everything ahead of time, it would be like a 100-hour week endeavor. And technically I'm in a 37-hour work week, although it's more like 90, but okay. Anyway, so murder and robberies. The first thing is to see if there's a relation between the variables. Always do what first? Scatter plot, people. Scatter plot, scatter plot, scatter plot. Look at the data. See what you got going on. Use your little eyeballs before you start calculating anything, right? Now I'm going to do murder as Y, robbery as X, but I got to tell you, I don't know what predicts what. Let's look at this. Scatter plot, I don't know why it's taking this long. It's running graph. I don't know why it's so ridiculously slow. SPSS does this sometimes. Like sometimes it's like speedy, and then other times it's like putz. Um, it says it's running. I don't know. I don't know why it would be so hung up doing such a very simple little graph. It doesn't seem to be liking me very much. Interesting. I don't want to mess it up because I probably will if I touch anything. Okay, here we go. So for some wacky and bizarre reason, like I had to close the old output and open a new output. I don't know. But we do see in this minuscule data set, which realistically you probably shouldn't use for a model, but it's textbook data, so you do see a linear pattern here. At least, if you kind of like you know so there is like a linear thing going on. Is it strong and convincing and humongous? No, because if we took out like one point here, it would be like different. But this does look promising though for us to be able to do a basic regression model. So next what we want to do is look at the correlation and its significance. Okay, analyze. Correlate has its own section because it's super duper important. Bivariate. um it doesn't even ask you for the difference between X and Y when you do this, by the way. So leave the defaults. You're doing a Pearson, you're doing a two-sided. This stuff, I don't even know what all this stuff does. Hit go, and we get a correlation metric of 0.804. That's pretty good, especially considering the size of the data. Significance is 0.016. It's significant. Is it strikingly significant? It's less than 0.05, but it's not like super duper less than 0.05. But anyways, it's good enough for us to do a regression model and get our equation for murder by robbery. So let's go back into the data. Um, Analyze, regression, linear. Go there. Okay. Now we have to know what the difference between our dependent and dependent is. Dependent is Y. What are we predicting? Murder. Sad but crazy. So robbery in this case, we're only working with one variable right now, so that's it. Okay. Hit go. This is going to give us our model. This we don't care about. This we don't care about. This we don't care about for now. This is what we want, which is our model. This is our model. By the way, it's this less than 0.05 that you care about. It's not really this. This is just the intercept, and all it's doing is testing whether or not the intercept is significantly different from zero. We don't care if the intercept's like different. We don't care. The intercept is just part of the equation. It's the slope and the influence of this variable and this significance we care about. So I now have a model which I can't write in SPSS because SPSS will not let me write. Um, and I don't have anything else I can write with because I don't have Word on this, I don't think. But anyway, so our model here is we look at the unstandardized. The standardized, some people use the standardized, I don't. I don't because that basically gets rid of the intercept, and I want the intercept in there, and I want it to look like y equals mx plus b, which is what you guys understand. So this is going to be murders is equal to 1.7 plus 0.026 times robbery. Murders is equal to 1.7 plus 0.026 times robbery. Your slope is 0.026, your intercept is 1.7, and you're predicting murders. And if you looked up here, if we could draw on this, that would be great, but we can't. And I don't think, unlike Excel, we can just shove a trend line on. I don't think like SPSS, Excel, you can just kind of like stick lines on things and like it's there. SPSS won't let you do that, and probably for good reason because you really shouldn't. Again, SPSS seems to have this disconnect between the graphics and the statistical output. But anyways, we have A, looked at the scatter plot of the data, B, done a correlation, determined that it's significant, and then C, fit a model where we get the slope and the intercept, and we can write the model out, and then we could use it to predict robberies based or murders based on robberies. Okay, so this concludes uh the first half of part 2 of the videos, and I'm pretty sure that you're totally ready to do your mod 2 problem set A. Okay. So The second part of this video will include some more stuff, but I don't think that's on the problem set A. I think it's on the problem set part B. But you're pretty set to start that problem set and work on that problem set 2A after watching this. Okay, thanks.